Hello, Algebra 2 class, and welcome back to another one of my HansenMATH video tutorials. In order to be ready for this one, which is the Continuity Learning Plan Lesson number 3, More Radical Trig, make sure that you either printed or are willing to copy down the guided notes, which I've attached to Google Classroom. You need something to write with, and you need a calculator. How we're going to do this is we're going to work together, and at certain points I'm going to tell you to hit pause, and you're going to move on your own volition. Okay, let's get started. When we last met, we were working on trigonometry, and I noticed a little bit of a hurdle simplifying square roots, which are also known as radicals. Now, a radical can be any index. It could be a third root, it could be a fourth root. A square root means that the index is 2, meaning that you're thinking about multiplying a number by itself. I noticed that a lot of people had some difficulties, so let's get some more practice in. Now, before we work on simplifying square roots, this is all based on understanding your perfect square numbers. So on your paper here, let's generate a partial list of perfect square numbers. Now, like a lot of lists of numbers, these go on infinitely forever, so we'll just do a partial list. Okay, here are your perfect squares. 2 squared, which is 2 times itself, is 4. 3 squared, 3 times 3 is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 times 9 is 81. 10 squared is 100. Okay, that should be plenty for this assignment. And let's see what's going on here. Okay, number 1 says that we want to simplify the square root of 20. Now, the reason it's not already simplified is because it contains one of these perfect square numbers. You want to find the biggest one of these that's contained in 20 and pull it out. So let's see, 20. Is 20 divisible by 4? Yes. Is it divisible by 9? No. Once you get up to a number that's more than half of the number, like 16 is more than half of 20, there's no point in even looking because there's no way it's divisible. So we'll say, okay, 20, you little weasel, you are the same as 4, which is the perfect square, times what? Now, the second number is not going to be a perfect square. It could be anything. So you're literally asking yourself, what is 20 divided by 4, or 4 times what is 20? And that would be 5. Now you take your perfect square, 4. The square root of 4 is an exact whole 2. The square root of 5, if you use your calculator, there is no exact value. The square root of 5, I can see right here, is 2.23606, blah, blah, blah. It goes on forever. So the whole point of this is to use exact values and avoid square roots. So the square root of 4 was perfect. It was a whole 2. The square root of 5 is irrational. It's decimals forever. So you just bring it down and leave it as the square root of 5. Okay. Number 2, we're going to break down the square root of 48. If you press the square root of 48 in a calculator, you get a decimal. We're avoiding all that. So let's see. Is 48 divisible by 4? It is 12 times, but there is a larger one. Is 48 divisible by 9? 48 divided by 9, 5.3. Is 48 divided by 16? Yes, it is, 3 times. So that's a combination. 48, you little weasel, you're nothing more than 16 times 3. Notice I have them both inside the radical. 16 is the perfect square. The square root of 16 is a whole 4. The square root of 3 is irrational. It doesn't have a nice whole value, so we just bring it down. Okay, that brings us to number 3. We're trying to break down the square root of 54. So you can say 54, are you divisible by 4? 54 divided by 4 is 13.5. If you get a decimal, keep going. 54 divided by 9. Yeah, we get 6. So I'm going to say, all right, 54, you're the same as 9 times 6. Okay, how do we know we picked the right combination? Well, on the second number, you can check again. No perfect squares will divide into 6. Nothing bigger than 6 will divide into it. So certainly not 16, not 9. You could check 4, but 4 does not divide whole into 6. So we're on the right wavelength here. The square root of 9 is a whole 3, and you bring down the square root of 6 for the ride. Okay, these are fully simplified because what's left inside of the square root cannot be further divided by any of these perfect square numbers. If what's left inside the square root can be divided by one of these perfect square numbers, you didn't break it down all the way, or in other words, you didn't find the largest one that goes into it. So at this point, what I'm going to do is I'm going to tell you to hit pause, and you're going to try 4, 5, and 6 on your own. And I'm going to check it when you turn it in when you're all done at the end. So hit pause, try 4, 5, and 6, and when you are all set, we shall resume on part 2. In part 2, we're going to practice another skill that I think we need some brushing up on. This is called rationalizing the denominator. There's an old-fashioned rule in math that says if you leave a radical or a square root in the denominator, like so, it's not fully simplified. So I'm going to refresh your memory on how to do this. Number 7 is a fraction, a whole 2 divided by the square root of 5. This square root of 5 is the problem, so you multiply by that very problem, the square root of 5, to the numerator and denominator. The reason you can do this is anything divided by itself is 1. You're not changing the value of the problem. So now you multiply straight across. 2 times root 5 is 2 root 5 over the square root of 5 times the square root of 5 is the square root of 25. Okay, now we'll simplify. We have 2 root 5 over this square root of 25. This is a perfect square. The square root of 25 is just a whole 5. Now, you may be tempted to simplify this square root of 5 and this whole 5, but don't be tempted because they're very different. This whole 5 is like $5. If you went to the store and they said, your total, please, will be 2 root 5, this root 5 is worth 2.23, much less than half of 5. So they're different. Do not mix roots with whole numbers. The last thing to check here would be, can you simplify the whole 2 and the whole 5? You cannot. They're called relatively prime. Nothing that divides into 2 also divides into 5. Now, it's worth checking because any number of things can happen here. Sometimes you'll have a problem that's 2 over 2. Those just cancel to 1. You could have anything happen, and we'll see what happens in number 8 if there's more simplifying. Sometimes there is, sometimes there is not. So this one is fully simplified. Okay, that brings us to number 8. We have 9 over 2 root 3. So the whole problem here is just this root 3. This 2 isn't the problem, just the root 3 because it's in the denominator. If it was in the numerator, you're cool. But if it's in the denominator, more work to be done. So you're going to take that problem child here, root 3. You're going to multiply it to the numerator and the denominator, and then multiply straight across. 9 times the square root of 3 is 9 square root 3 over 2 root 3 times root 3. You keep your whole 2, and then the root 3 times root 3, 3 times 3 is root 9. Now let's simplify it some more if we can. We have 9 root 3 over 2 times the square root of 9 here. The square root of 9 is a perfect square. Square root of 9 is a whole 3. So now we have 9 root 3 over 2 times 3 is 6. And now we check the same thing we did in problem 7. In problem 7, remember the 2 and the 5 were relatively prime. They didn't simplify. But here, the 9 and the 6, they share a common factor. They're both divisible by 3. So you say, all right, 9, you little weasel, you're divisible by 3. 3 goes into 9, 3. Bring down your root 3 over. 3 goes into 6 twice. Now 3 and 2 are relatively prime. Nothing that divides into 2 divides into 3. You are done. So that was 2 examples of rationalizing the denominator. I'd like you now to hit pause and try 9 and 10 to the best of your ability on your own. Good luck, and when you're done, undo pause and we'll move on to part 3. In part 3, we're going to review trigonometric ratios, which are sine, cosine, tangent, and the reciprocal ones, cosecant, secant, and cotangent. This went pretty good, but there were some problems on the last assignment. So let's brush it up a little bit. So here you have a right triangle. Here's your right angle. You have one leg is 12. This leg is 5. The hypotenuse, which is like the ramp, it's the biggest side across from the 90 degree, it's unknown. So we'll find that first using the Pythagorean theorem. So the Pythagorean theorem says a squared plus b squared equals c squared, or leg squared plus leg squared equals hypotenuse squared. Well, the legs, they make this L frame. So your legs are the 5 and the 12. So we have literally 5 squared plus 12 squared equals c squared. Crunch it out. 5 squared means 5 times 5, which is 25, plus 12 squared, 12 times 12, 144, equals c squared. Combine 25 plus 144 is 169, equals c squared. Take the square root of both sides. Now, before you start dividing by those perfect squares to break it down or simplify, when it's a big number like this, you can hope and cross your fingers that maybe 169 is a perfect square. So in my handy dandy calculator, when I do the square root of 169, lo and behold, it's a exact 13. So the square root of 169 is just 13, because 13 times itself gets you back to that. That is the length of C, which is the hypotenuse. So now I can add this to the picture. The hypotenuse is 13. Okay, where do we go from here? Well, in the picture, we know this is the right angle here, but this is theta. Theta means an unknown angle. That's our reference angle. So we know that this is the hypotenuse. Like I told you on the last assignment, the adjacent always connects this theta to the right angle. So this is your adjacent. So I'll call that A for adjacent. The opposite is the furthest side away from theta. It goes through the triangle out the other way. So that's your opposite. The opposite does not touch the theta, as the hypotenuse does, and the adjacent does. The opposite, does not. Okay? So now that we have opposite, adjacent, and hypotenuse labeled, we should be able to do this. Now, it might be helpful for you to write down the little jingle, so katoa. So that's a little jingle. That means sine is opposite over hypotenuse. So sine is opposite over hypotenuse. And in specific, it was 5 over 13. Boom, done. Cosine is a fancy word for, here's the C in ka, C for cosine, adjacent hypotenuse. Adjacent over hypotenuse, so that would be 12 over 13. Done. Tangent is a fancy word for tangent, T for tangent, opposite over adjacent. Okay, look at your picture. The opposite was 5. The adjacent was 12. Done. Cosecant. Cosecant is related to sine. It's the reciprocal of sine. So if sine was OH, cosecant is H over O. So it's just the flip. So if sine was 5/13, this is 13/5. Secant is related to cosine. They're reciprocals. So if cosine was A over H, this is H over A, which is 13 over 12. Again, you can see here, I'll make some little loops. These guys are related. These guys are related. And you can probably guess that the last one is going to be cotangent is related to tangent. If tangent was OA, this is A over O, which is 12/5. All right. So that was a little bit of a review. Hopefully that helps it sink in better. We are ready to move on to part 4, the last part. Part 4 is let's put it all together. So here are the directions. This is something new, so let me help you through it. Number 17 says, given the point -2, 5 is on the terminal side of an angle in standard position, provide all 6 trig ratios. Okay? So what you need to do first is on your little graph, you want to put in some hash marks so we can plot the point -2, 5. Okay, -2 for the x means we're going to go to the left, and 5 positive on the y means we're going to go up. So if we go left and up, we are in quadrant 2. So I'm going to put in some hash marks on quadrant 2. Okay, and we'll plot our point. So we're going to go left 2, up 1, 2, 3, 4, 5, right here. Okay, that's -2, 5. And what we're going to do next is the following. The terminal side of the angle means you connect the origin to that plotted point, okay? But that's not an angle, my friends, that's just a ray. An angle consists of 2 rays. The second ray, which is called the initial side, always lays on the x-axis. The other ray, called the initial side, always lays on the x-axis. So that one is going to be length -2, really length 2. Negative means it goes to the left. So I'm going to draw that in here. Okay? So again, where is that coming from? That's coming from the -2 on the x. Okay? This here, I don't know what its length is because it's going on this slant, but I'm going to drop down a vertical line, and I know what that length is. That's the y coordinate. Okay, this is the y, this was the x, that's +5. All right, so the the -2 is coming from the x, the +5 is coming from the y. I'm going to put in theta. Theta touches the origin, essentially, right there. And we're going to say some things about this. We're going to do trig. We're going to do sine, cosine, tangent, cosecant, secant, cotangent. But first, we need to find the hypotenuse because it is unknown. Well, this is like we did in the previous examples. We're going to use Pythagorean theorem. A squared plus b squared equals c squared. A and b are the legs, so it's the -2 and the 5. So we've got -2 squared plus 5 squared equals, we don't know, c squared. Crunch it out. -2 squared, -2 times itself, +4, plus 5 squared, 5 times 5, 25, equals c squared. Simplify. 4 plus 25, 29, equals c squared. Take the square root of both sides. So plane C equals the square root of 29. Now, you can try to break this down. You can go back to those perfect squares. Is 29 divisible by 4? Is 29 divisible by 9? Is 29 divisible by 16? It turns out it's not, it is a prime number. It's divisible by nothing but 1 and itself. So this is the length. Okay, right here I'll put in an arrow. The hypotenuse is length root 29. Now, you may not convert it to a decimal. If you do that, I'm going to return your assignment back to you and tell you to redo it. So I'm going to tell you right now, no decimals on this assignment. No, 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 not accepted whatsoever. That's the whole point of this, is to practice using radicals, also known as square roots. Okay? So let's diagram this now like we did prior. The side that connects theta to the 90-degree angle, that's always the adjacent. So -2 is the adjacent. This 5 here is the opposite because it's across from theta. And this root 29, which you're not going to turn into a decimal, is the hypotenuse. So now we should be ready to rock and roll. Sine is opposite over hypotenuse. So that would be 5 over root 29. But guess what? We're not going to leave it like this because we practiced rationalizing the denominator in part 2. So now you know that this problem child down here, root 29, you got to multiply that to numerator and denominator, and then you'll get 5 root 29 over a whole 29. Okay? Now you can try to simplify further. Does 5 go into 29? It does not. So you are done. You're done. Now, I think it makes sense to do cosecant now, since these are reciprocals. So cosecant is hypotenuse over opposite. Go back to the beginning. If it was 5 over root 29, flip it. So now it's root 29 over 5. Hey, the square root is on the top. That's cool. You're done. You're just done. Okay? Move on to cosine. Cosine is adjacent over hypotenuse. Well, what do we have? The adjacent is -2. The hypotenuse is root 29. Okay, problem. It's in the bottom, or the denominator. Multiply the problem, root 29, to top and bottom. So you get -2 root 29 over a whole 29, because root 29 times root 29 is the square root of, let's see, 29 times, that's the square root of 841. Then if you take the square root of 841, you're right back to 29. Okay? Again, you're done because 2 does not divide into 29. Can't be simplified further. Might as well now do secant, because these two are reciprocals. They're related. If cosine is a over h, secant is h over a. Go back to the original fraction. Instead of -2 over root 29, flip it. Root 29 over -2. Is the square root in the bottom? Nope. So you're done. It's perfect. All right, keep it moving. Last pair, tangent. Tangent is opposite over adjacent. So in specific, that was from the problem here, 5, over here, 5 over -2. You cannot simplify because 2 does not divide into 5. They're called relatively prime. Okay, cotangent is the reciprocal. Instead of O over A, it's A over O. So just flip it, reciprocal. These are related. So it's -2 over 5, and you're done. Those are your 6 trig ratios. Moving on to number 18. It's really the same type of problem, except for the point has changed. 5, -3 is on the terminal side of the angle. Provide all 6 trig ratios. So again, I'm going to make a little hash marks, but before we do that, I'm going to figure out where we are. 5 is positive, so that means it's going to go to the right, and 3 is negative, so since that's the y, it's going to go down. So if we go right and down, we're in quadrant 4, so I need to go 5 to the right and 3 down. So 5 right, 3 down. My terminal point is going to be right here. So now I can draw my ray, okay? But I also need the initial ray, which lies on the x-axis, okay? So there's my initial ray. That was a length of 5. Now I'm going to close it down with a leg here. That was a length of 3, but since it's below the x-axis, it's -3. You got to make sure you obey the signs here from your point. And the hypotenuse is missing. I can put in my theta, that goes right here. It always goes closest to the origin. So you can probably figure out that this is the adjacent because it's laying on the x-axis. It connects to the right angle. Theta to the right angle, that path is the adjacent. This is the opposite. This is the hypotenuse, but it's unknown. So I'm going to stop here. You at home are going to do Pythagorean theorem to get h. You're going to work on these 6 trigonometric ratios, simplifying, rationalizing them as needed, and you're also going to do number 19. When you're done with the whole thing, scan or take a pic of it, upload to Google Classroom, and you are all good in the hood. So good luck to you guys. Remember, it's always a great day to be a pioneer, and I hope this video helped. This is going to keep you sharp for the fall, especially if you're going on a pre-calc. You need this. So do the best you can. Come to my office hours or email me if you need help, and have a wonderful day. Thanks so much.